Welcome students. Today class is likely to be devoted to linear programming, and right from today I am starting linear programming. Now regarding linear programming, in 1947 an American defense personnel GB Danzig gave simplex method which was made public in 1951. So the first algorithm for LP linear programming was given by this G.B. Danzig in the year 1947, which was made available for the public in 1951. Now, how this LP came into existence? So, Danzig and his associates observed in a military storeroom or the defense storeroom, he observed that most of the military management and planning problems could be formulated as maximization, minimization of a linear objective function called objective function. This objective function is subjected to a linear constraints in variable and it is called set of constraints. So, Danzig observed these two phenomena, and then by observing these two phenomena and by realizing that this could be formulated in the form of a sum, and it was given the name linear programming because all the relations are in linear form. And what linearity means, a1 x1 plus a2 x2 plus a3 x3 dot a1, this is linear because all variables are raised to the power 1. And in this equation, a1 to an are the constants and x1 to xn are the variables. So now, linear means all the relations are linear. That is why linear. And what this word means, programming. So programming refers to the process of determining a particular program or plan of action. This is what programming means. So now, just we can define LP. That LP calls for optimizing a linear function of variables, that is called objective function. LP calls for optimizing a linear function of variables subject to a set of linear equations, of course in the form of inequalities, and this is called set of constraints. And in fact, this linear programming is one of the most important optimization technique developed in the field of OR, though this LP technique has been developed much more than what it was in the 1947 and 1951. So now this is a little historical perspective of this LP. Now we must see what are the different components of LP that we shall see right now. Now initially LP was formulated, but as of now non-linear programming has also been developed as per the need of the organization or the need of the situation. And in this non-linear programming, we have the various forms: quadratic programming, separable programming, geometric programming, fractional programming, dynamic programming, and there are various forms of this non-linear programming too. So this is the history of LP and non-linear programming. Now, as far as the components of LP is concerned, primarily an standard LP sum has three components: objective function, set of constraints, and restrictions. If we are dealing with the maximization program, then we shall have inequality in the form of less than or equal to, and if we are handling minimization program, then we have greater than or equal to. So this will be the form of, though in some sums or in some numericals we shall have all. Those are the complex sums. So, but generally on an average, maximization contains less than or equal to, minimization have greater than or equal to. Now, just I am citing two examples. This is maximization of profit. This is the objective function. And this is set of constraints. And this is restriction. Absolutely, if it is a maximization program, we have a less than or equal to inequality, and this is minimization, minimizing cost. Minimize cost 6x1 plus 21x2. These are the two constraints. This is restrictions, and in the constraints we have inequality in the form of greater than or equal to. So this is objective function, this is constraints, and this is restriction. So this is what the general feature or the general look of a standard LP sum is. Now as far as the solution of LP is concerned, we have two methods for finding solutions of LP. One is the graphical technique, where we can at most handle only two variables, and most universal and popular, that is simplex method, it could handle n variables. We shall see both of the technique. So for finding solution of LP, we have the two technique, graphical and simplex. In graphical, we are constrained by two variables only, whereas in the simplex case, we can handle n variables at a time. So this is what about the solution of LP. Now, next I would like to show you formulation of LP sum. Formulation of linear programming problem, how from the given theoretical language LP sum is being found out. A few examples I am going to show in the class. कितना देर हुआ है? Now this sum says that a firm produces two products A and B, right? This firm is just producing two products A and B. Profit on A is ₹2 and on B is ₹3. That's fine. So profit on A is ₹2 and profit on B is ₹3. Each product is produced by two machines, G and H. Now product A requires 1 minute of G and 2 minutes of H. This is a requirement of X1. Whereas B requires, this X1 has been taken for A and X2 for B. And B requires 1 minute of G and 1 minute of H. Now the firm has the utmost available quantity of G and H is, G is available for 6 hours 40 minutes. Everything is given in minutes, so this 6 hours has to be converted into minutes. So 6 hours 40 minutes becomes 400 minutes, and this is 10 hours, it becomes 600 minutes. So now this is just in a tabular form. It can be converted into LP problem. So maximize profit 2x1 plus 3x2 subject to 1x1 plus 1x2, that is x1 plus x2 less than or equal to 400, and 2x1 plus x2 less than or equal to 600, and x1 and x2 is non-negative. So this has become a perfect LP problem. This is objective function, this is set of constraints, and this is non-negativity restriction. So this is how any theoretical sum can be converted into a LPP. Now let me take another example. This is the second sum. A company produces two types of hats, A and B. Each hat of the first type requires twice as much labor time as the second type if all hats are of the second type only. The company can produce a total of 500 hats. The market limits first and second type of to 150 and 250. Profits on those both A and B hats are ₹8 and 5. Formulate LPP. Obviously, we are given the profit, so this relates to the maximization program. So maximize profit. Now type A we let x1 and type B we let x2. So the profit on A is 8. So 8x1 plus 5x2. Now subject to each hat of the first type requires twice as much labor time as the second type. Yes, so 2x1 plus x2, and what is the limit? Probably it is 500 hertz. Yes, so it is less than 500. Now the market gives a cap on the first and second hat. The first and second hat 150 and 250. So the firm can produce first hat not greater than 150 and second hat not greater than 250, and x1 and x2 is non-negative. So this is standard sum, and it is a maximization program, and the moment we get the profit, it relates to the maximization of profit. So maximized profit 8x1 plus 5 is these 8 and 5, where the respective profits on 1 unit of x1 and x2, and this is 3 constraints as per the sum given here. So this is a standard LP sum. Now it could be solved either through the graph or through the simplex method, that we shall see later on. One more sum of minimization I am going to show you. Now this is the third sum, and this relates to the minimization program. A farm breeds pigs. They are fed 3 feeds, X, Y and Z. Farm purchases 2 products, X1 and X2. Now 1 unit of x1, these two products x1 and x2 contains xyz feed. Now 1 unit of x1 contains 36 units of x, 3 units of y and 20 units of z. 1 unit of x2 contains 6 units of x, 12 units of y and 10 units of z. The minimum requirement of x, y, z are 108, 36 and 100. Product x1 cost 20 per unit and product x2 cost 40 per unit. Formulate LPP. Definitely, since cost is here, so we are concerned with the minimization program. So let us make a table. We are having two products, x1 and x2, and each product contains 3 constituents, x, y and z. This x1 product has this constituent in the form of x, y and z. It is given right here, and x2 contains these 3 constituents like this. This is 2 given here. Now the cost of x1 is 20, cost of x2 is 40. In the feed, the minimum requirement of x is 108 units, minimum of y is 36 units and z is 100 units. So now this could be shown in the form of a standard LP sum. So minimized cost of A is 20 and cost of B is 40 per units. So minimized cost 20x1 plus 40x2, 20x1 plus 40x2. This is the cost function, this is objective function. And now from this table we are supposed to make the constants. 36x1 plus 6x2 less than or equal to 108, 3x1 plus 12x2 less than or equal to 36, and 20x1 plus 10x2 less than or equal to 100. So these are the 3 constraints, and x1 and x2 is non-negative. So once again, this is objective function, this remains constraint, and this is restriction. So this is how any theoretical sum related to OR could be converted into LPS. I have shown 2-3 examples. You do on your own practice. If you are having any problem in just formulating the sum, you put the sum just in the discussion, and I will solve in the class. Now from next class we shall be starting graphical method of solving LPP. So next class will be of graphical method, and this is what for today. Thanks.